Welcome back. In this part of our deep dive, we're going to unlock the secrets of nuclear energy. And we're going to start with a really strange puzzle, one that's right at the heart of the atom and seems to break a fundamental rule of physics that we all learned back in school.
You know, from our very first science classes, it's drilled into us mass is always conserved. You can't just create it or destroy it. But, in the wild world of nuclear chemistry, the rules get a little weird, and things don't always add up the way you'd expect.
So, let's play detective and solve this mystery. We'll start by building something simple, a helium nucleus, from its basic parts, 2 protons and 2 neutrons. Now, on paper, the math should be super easy, right? But as you're about to see, reality has a little surprise for us.
Okay, check this out. If we take the mass of 2 separate protons and 2 separate neutrons and add them all up, we get an expected total of 4.031880 atomic mass units. But, and here's the puzzle, when we actually measure a fully formed helium nucleus, its mass is only 4.001503 units. It's lighter. Some of the mass has just vanished. The whole is literally less than the sum of its parts.
That tiny little difference, just about 3/100ths of an atomic mass unit, that's our missing mass. And in nuclear physics, this has a name. It's called the mass defect. I know it looks like a tiny, tiny number, but believe me, its implications are absolutely enormous.
So the big question is, where did that mass go? It didn't just disappear into thin air. The answer to this puzzle was figured out by one of the most famous scientists in all of history, and it completely changed how we understand the universe.
Yep, the key was unlocked by Albert Einstein, with an equation so elegant and so powerful it would come to define the 20th century and give us the key to the power of the atom.
You know it, you've seen it everywhere. E equals mc squared. This is the principle of mass-energy equivalence. And what it tells us is that mass isn't really lost, it's just converted directly into energy. Turns out, they're 2 sides of the same exact coin.
So let's use this equation to solve our helium mystery. E, that's the binding energy we're looking for. M is our mass defect, that tiny 0.030377 number. And then you have c squared. That's the speed of light squared, and it's an absolutely colossal multiplier. It's the real powerhouse here. When you plug in the numbers, that tiny sliver of missing mass converts into about 4.54 times 10 to the negative 12 joules. Okay, that sounds small, but remember, that's for one single nucleus. To put it in perspective, the energy from just 1 gram of that lost mass is enough to power a large city for hours. This energy is the cosmic glue holding the nucleus together, and it's the source of all nuclear power.
So, this is the main takeaway here. This binding energy, this converted mass, is the fundamental source of all nuclear power. When we talk about harnessing the power of the atom, what we're really talking about is finding clever ways to release this incredible energy. Okay, so how do we get this energy out on a large scale? Well, the first method humanity discovered was basically by breaking things apart, a process called nuclear fission. Fission is pretty much exactly what it sounds like, splitting something. You take a big, heavy nucleus like uranium-235, you hit it with a neutron, and it becomes really unstable. It shatters into smaller elements, and when it does, it releases more neutrons and a huge burst of energy. And then, those new neutrons can go on to hit other uranium atoms, creating a chain reaction.
Now, the star player for fission is uranium, but there's a catch. The most common type, uranium-238, which makes up almost all of it, is pretty stable. The special isotope we need, uranium-235, is actually really rare, less than 1% of all uranium. Now, that word fissile just means it's the kind that can be split by a neutron and release more neutrons to keep that chain reaction going. Its rarity is why uranium has to be enriched for reactors, which is basically just increasing that U-235 concentration. But that really common U-238 isn't totally useless. It's actually got a neat trick. Inside a reactor, it can absorb a neutron. Then it undergoes a couple of beta decays. That's where a neutron inside the nucleus literally turns into a proton. This process actually changes the element itself, first into neptunium and then into fissile plutonium-239. So in a way, nuclear reactors can actually breed new fuel while they're running. Splitting atoms apart releases a staggering amount of power. But what if we could do the complete opposite? Let's talk about the process that powers the stars themselves, nuclear fusion. So yeah, this is nuclear fusion.
Instead of splitting a heavy atom, we take two super light ones and, under insane heat and pressure, we force them to merge into one heavier nucleus. And just like with fission, the final product has less mass than the parts you started with, releasing an even greater amount of energy.
The main fuel for fusion comes from the lightest, most abundant element in the whole universe, hydrogen. But specifically, we use its isotopes, deuterium, which has one extra neutron, and tritium, which has two.
So, for example, a simple fusion reaction might involve a regular hydrogen atom fusing with a deuterium atom. And the result? You get an isotope of helium, called helium-3, plus a burst of energy.
But here's the one scientists are really excited about, the one they're trying to harness for clean energy. This involves fusing deuterium and tritium. This creates a really stable helium-4 nucleus, kicks out a spare neutron, and unleashes just a massive amount of energy.
Now, this idea of fusion, it isn't some abstract theory we just cooked up in a lab somewhere. This is a process that's happening right now on an unbelievable scale all across the entire universe.
That's right. Every single time you step outside and feel the warmth of the sun on your face, you are feeling the energy from countless fusion reactions happening millions of miles away. The incredible gravitational pressure at the core of a star creates the perfect furnace, constantly smashing hydrogen atoms together to forge helium and releasing the energy that makes all life on Earth possible.
Now, if we want to achieve fusion here on Earth, we basically have to try and replicate those star-like conditions. That means heating the fuel to millions of degrees Celsius, creating a fourth state of matter called plasma, where it's so hot the electrons are literally ripped away from their atoms.
As you can imagine, trying to contain something that's hotter than the sun is a massive engineering challenge. Huge international projects like ITER in France use incredibly powerful magnetic fields to create a kind of magnetic bottle. And while they have successfully achieved fusion, they haven't yet reached that all-important break-even point. That's the moment where the reaction finally produces more energy than we have to pump in to get it started.
And that really brings us to our final thought here. Fission is the nuclear technology of today. It powers our cities, but it also creates long-lived radioactive waste. Fusion, on the other hand, holds the promise of nearly limitless, clean energy using fuel we can get from seawater. We have truly mastered the art of splitting the atom, but the ultimate prize for humanity? It might just be in learning how to build them, just like the stars do.